In section 3.4, we're going to look at the concept of continuity of a function. Now, from an informal point of view, the concept of continuity is a very simple one. If you can draw a function without ever lifting your pencil off the paper, then you have what's called a continuous function. For example, I've drawn three different graphs here. This would be a parabola, a degree 2 polynomial. When you draw this graph, you'll notice that you never have to lift your pencil. If you put your pencil right here and just drew the graph, it's just a nice smooth graph. You never have to ever lift your pencil off the paper. That's basically what continuity means. So I've just drawn a couple of examples here for you. This would be a quadratic function. This would be a linear function. So basically any polynomial. In B30 you studied cubics and quartics and quintics, degree 1, 2, 3, 4, 5, that kind of thing. Anytime you have a polynomial function, polynomial functions are always continuous. This is a function that you may or may not have seen yet, depending on if you finished your C30. This is a trigonometric function. This is a sine wave, and sine waves would be another example of a continuous function. If you put your pen right here and just drew a curve, you'd never have to lift your pencil off the paper, and you'd have a continuous function. So from the informal point of view, this idea is very simple. We're going to look at it from a little bit more of a theoretical point of view, and it's going to involve the concept of limits. To begin our study of continuity then, let's take a look at a very simple example. I like to use this example just because of the ease of graphing it. This is a quadratic function, and as I'm sure you know, a quadratic function is a parabola, and the parabola in this case has a vertex at the origin. So what we have here is just a curve that comes down like this, opens upward, and travels on forever. So that would be the graph of our quadratic function. Now let's say we were interested in asking ourselves this question. What if we want to know what's the limit as x approaches 2 of this function f of x? So if you look at the graph, x equals 2 would be over here somewhere. This might be x equals 2. This would be the y value. The y value would just be what you get when you plug 2 into the function. In that case, it would be 4. You may recall from our strategies of limits, in this case, we could just use direct substitution. We could just plug the number 2 into the function, get the answer 4, and so we know that the answer here is indeed 4. But why were we able to do that? Why were we able to make a direct substitution? It's because if we looked at this from each side, if we actually said, what's the limit as x approaches 2 from the right of this function? If you're coming in toward 2 from the right, so you're coming in this way, you obviously would be approaching this point right here. So the limit would be 4. If you were to come in toward 2 from the left of this function, so if you're coming in this way, you also would be approaching the same number 4. But here's the really important part. Remember that limits only ask the question, what's happening as you approach a point? So this is saying that as we come in toward 2 from both sides, that we're approaching the number 4. But in this case, we actually get to that point. Remember that for a limit to exist, you don't have to actually reach that point. You just have to be approaching it. But in this case, and this is very important, note that if you actually took the number 2 and plugged it into the function, you would get 4. So what's happening is the limit that you approach as you get closer to 2 is actually equal to what's happening right at 2. And that's the definition of continuity. We would say that this function f of x is continuous at x equals 2 since, and this is now going to be our definition of continuity, and I'll give you the definition in a moment, but the reason why our function is continuous is because the limit as we approach 2 of this function is equal to 4, but that's also equal to the function right at that point, which is 4. So here's the definition of continuous. A function is continuous at some point x equals b if the limit as x approaches b of the function is equal to the function at b. That's our definition of continuity. So we start off by talking about it from an informal point of view, where you just basically, you don't have to lift your pencil off the paper, but mathematically what's happening is that the limit at a point is actually equal to the function at that point. Now what we're going to do is we're going to look at different categories of where functions are discontinuous. How can that possibly happen, and what would it look like? Okay, so we're going to start now by classifying different ways that functions can be discontinuous. And the first one is called an infinite discontinuity. And that's going to happen in functions that we saw earlier. They're called rational functions. If you have a function like f of x equals x plus 2 over x minus 4. Now, obviously at the point 4, this function has a problem, because if we were to let x equals 4, we would end up with 6 in the numerator, but we'd end up with 0 in the denominator. Now, hopefully you recall from our earlier discussions that if you have a number that's not 0 in the numerator, but 0 in the denominator, then what you have is a vertical asymptote. So what's happening here is, if you were to draw this graph, is that at x equals 4, the graph doesn't exist. There's a vertical asymptote at x equals 4. In this case, the graph would come up like this from the right and come down like this from the left. If you were drawing this graph, you notice that you'd have to lift your pencil off the paper. You'd be coming up like this. You'd eventually go off toward infinity, but at some point you'd have to lift your pencil off the paper, come back down here, and continue on along your graph. So obviously this function is discontinuous. So we would say that f of x is discontinuous at x equals 4. And the type of discontinuity is called an infinite discontinuity. So we would say f of x is discontinuous at x equals 4. We would call it an infinite discontinuity. And you always know you have an infinite discontinuity if you have 0 in the denominator and a number on top. So infinite discontinuities always happen when you have something like b over 0. Now remember, a moment ago I gave you the definition of continuity. If you wanted to prove that this was discontinuous other than just drawing a picture of it, we could use our definition. The definition is that if a function is continuous at a point, then the limit should equal the value of the function at that point. Well, the limit as x approaches 4 of this function does not equal the function at 4. The function at 4 doesn't even exist. There is no answer. And so the two quantities are not equal. That's how mathematically we would show that it's discontinuous. So the first category is called infinite discontinuity, and it occurs when you have what's called a vertical asymptote. The second category is called a jump discontinuity. And we're going to see those in those functions that we call piecewise functions. Now, I'm not going to actually do an example of a function. I'll just show you what it would look like with a picture. We've done this earlier. If you had a graph, and let's say this was some point right here, and this point was x equals a. And our graph looks something like this. Okay, so that's just an example of a piecewise function. It would just be some function f of x that's equal to, and then you'd have your brace, and there'd be two different formulas depending where you are on the domain. We saw this when we were doing our strategies for limits. If the functions don't meet, the two pieces of the function don't meet, then obviously there's a jump. If you were drawing this with your pencil, you'd be coming down like this, you would jump up to this point, and you would continue along. So our function definitely is discontinuous here. This point right here, let's say this point was L. Our function f at the point A, right at this point x equals a, our function does exist. It would actually be L. But the limit as we approach a of this function does not exist. The two one-sided limits are not the same. And that's the definition of continuity. If you don't get the same answer when you plug the number in as when you approach that number, then the function is said to be discontinuous. So the way you test for a jump discontinuity is you're going to have a piecewise function. You're going to just plug numbers into both functions depending where you are in the domain. And if you get different answers, then you know that the functions didn't meet at that point, and you have what's called a jump discontinuity. So let's do an example of a jump discontinuity. So what I've given you here is a function f of x, and it's equal to, and this is a piecewise function. The function is equal to x squared whenever x is greater than or equal to 2, but it behaves differently when x is less than 2. And what we want to do is we want to determine, does this function have a place where it's discontinuous? Well, these are both polynomial functions, so we don't have to worry about them being continuous or not. We know that all polynomial functions are continuous. But what about where they meet, or where potentially they don't meet, at x equals 2? So all you would do here is ask yourself, what's the limit as you approach 2 from the right of this function? If you come in toward 2 from the right, then the function is behaving as if it was x squared. So you would just plug 2 into x squared, and the limit would be 4. If you came in toward 2 from the left, you would have to plug in the number 2 into this function, and you would get 3. Now, since the limits are different, we would say that the limit as x approaches 2 of this function does not exist. The functions are not meeting each other. There's a jump between the 2 points. If you actually plug the number 2 into the function, notice that this function is actually defined for x equals 2, this one up here. So if you actually took the function f and plugged 2 in, you would plug it into this one and get 4. Since the function at 2 does not equal the limit as you approach 2, we would say that this function is discontinuous. So we would say that there is a jump discontinuity at x equals 2. Okay, our next method, our next type of discontinuity, and this is the one that's most important to us. This is the one that we're going to see when we get into the actual calculus part of the course, is going to be the one that we deal with all the time. This is called a removable discontinuity. And removable discontinuities occur whenever you have limits that are indeterminate. Whenever you have that 0 over 0 situation that we've seen so much of, you're going to have what's called a removable discontinuity. The graph, as opposed to these functions up here, the jump discontinuities where the graphs don't meet, like in this case right here, the graphs, one's coming up this way and one's coming down this way, and they're not meeting. In this case, what's going to happen, in all of the removable ones, the graph's going to look like this. You're going to have a nice, smooth, continuous graph, but there's going to be a hole or a gap in it. And that gap means that there's going to be a limit. The limit's going to exist, but you won't be able to plug the number in right at that point. And as you're going to see later on, this is really the key to what we're going to be doing. So for example, let's say we had the function f of x equals x squared minus 1 over x minus 1. And we asked ourselves the question, is this function continuous, or are there any points where it's discontinuous? Well, we look for trouble spots. In this case, the trouble spot is x equals 1. Obviously, if we plug 1 into here, we're going to get 0 over 0. So something is happening at x equals 1 that's giving us some concern. Using a method we learned earlier, the factoring method, we can expose the problem. The problem is that if we factor this, we can see that there's an x minus 1 over an x minus 1. Those are going to divide out. And so really what we have here is just a linear function. If you were to graph this function right here, it would just be a straight line. Except when x is 1, there would be no point there because it's undefined. When x is 1, this function would take on a value of 2. So at 1 and 2, there would be a gap or an open circle or a hole. Other than that, the graph would just be behaving like it was the graph x plus 1. That's what our graph would look like. Now this function is obviously discontinuous. If you were drawing it, you'd have to lift your pencil off the paper, jump over the hole, and continue on. So we know it's discontinuous. But what kind of discontinuity is it? It's removable, because we can actually divide out these common factors and remove the problem. And so we end up with a hole there, and it's called a removable discontinuity. So we would say that this function is discontinuous at x equals 1, and we would call it a removable discontinuity. And you know you have a removable discontinuity if you have the situation 0 over 0. So let's just wrap up this section then with an example. And what I'll do here is I'll draw a picture for you. And on this picture, I'll just try to illustrate all the possible discontinuities that we've seen. So let's say we had a function that was doing something like this. Let me first of all give myself a scale here to work with. And let's say we had a function that was coming up like this, and then there was a gap or a hole, and then it kept going up to here. And then we'll have it travel up to here with another hole, and then we'll put a point right here, and then we'll do something like this. What I've tried to do here is, this would be an example of a piecewise function. So this is some function f of x, and basically it's just a function that's behaving differently depending where you are in the domain. It starts out like a straight line, it changes into a parabola, or maybe a rational function, and continues on over here. From this picture, I would want you to be able to tell me, where is this function discontinuous? Now again, it's easy to tell by just the pencil test. If you're just coming along like this, you'd have to jump over this point, you'd have to jump to here, you'd go off to infinity, jump down to here. So obviously the graph is discontinuous. I just want you to be able to tell me what kind of discontinuity it is. So for example, at this point right here, at x equals -2, at -2, we have a gap or a hole. That's called a removable discontinuity. At this point right here, x equals 1, there's a jump. The graph is actually making us jump, so we would call this a jump discontinuity. And at x equals 3, the graph is heading off to infinity, and so we call this an infinite discontinuity. I thought I would finish off with one more example of discontinuity. On a test, you're more than likely going to have to determine the nature of the discontinuity by the actual function itself. So what I thought I'd do is just take you through a situation where you have to do that. So the instruction would be determine and classify the discontinuity. I want to know, where is the function f of x discontinuous, and what kind of discontinuity is it? Now it's really quite simple. There's only 3 categories, and what you're looking for, and I'll try to summarize that for you here, is the following. We're looking for a place where this graph might have a break or something wrong with it, and so what we do is you look for, in this case, the denominator being 0. The denominator would be 0 at x equals 2. So we know we got a potential problem there. The function doesn't exist. Now you need to classify the discontinuity. So we know it's going to be discontinuous at x equals 2. And the way you tell is by what happens when you plug 2 in. If you plug 2 in and you get 0 over 0, which is what's going to happen in this case, then you know you have a limit of indeterminate form, and it can be removed by factoring. So in this case, if I factor out x minus 2 from the numerator and x minus 2 from the denominator, I've removed the discontinuity. So you know you have a removable discontinuity whenever you end up with 0 over 0 when you make a substitution. So we would say that this function is discontinuous at x equals 2, and it's removable. So very simple to determine that. If you get 0 over 0, it's removable. For our next example, we're going to have something, a piecewise function. And again, I think you're going to find that these are very simple to determine. We want to know whether this function is discontinuous. Well, the only place we have to look is at 1. We know that these are both lines, and so they're going to be continuous throughout their entire life. But since the function is changing its behavior at 1, our attention is drawn to that point. So what we do is we just plug 1 into both of them. If we plug 1 into this function, in other words, if we take the limit, what's the limit as x approaches 1 from the right of this function? Well, from the right, it's behaving like 3x plus 1. So we're going to get 3 plus 1 is 4. If we ask ourselves what's the limit as x approaches 1 from the left of this function, we'd have to plug the 1 into here, and we'd end up getting 1. The two graphs are missing each other. At x equals 1, one of them is approaching 4, one of them is approaching 1. So there's a jump. So what we have here is a jump discontinuity at x equals 1. So we would say it's discontinuous at x equals 1, and we would classify it as a jump discontinuity. And our final example, f of x equals x over x minus 2. Again, we're drawn to the denominator. What would make that 0? Well, what would make that 0 is the number 2. So we know there's going to be a discontinuity at 2. But in this case, we don't get 0 on the top. If we plug 2 into here, we get 2 over 0, which is not called indeterminate. 2 over 0 is an infinitely large number, and so we classify that as, we know that's going to be an asymptote. So what we have here is a discontinuity at 2, and this would be our infinite case. So very simple to determine discontinuities. 0 over 0 is removable. Piecewise functions are functions that are potentially jump discontinuities because they're not meeting each other. And a number over 0 gives you what's called an infinite discontinuity.